Hi, I'm Alistair, and in this video I'd like to teach you some projects you can create using one of these ESP-32 CAM boards. Now what is this? Well, this is a board that has a tiny digital camera sensor on the top there. It also has an SD card reader and it's powered by an ESP-32 chip. Now that's a programmable microprocessor, very similar to an Arduino if you're familiar with those. It's actually a little bit more powerful than most Arduinos because it also has built-in Wi-Fi and built-in Bluetooth, and it has touch sensors and also a number of GPIO pins as well. So that means you can add on additional inputs and outputs that adjust how the camera behaves. So the camera itself is not that great quality. It takes pictures at a resolution of 1600 by 1200 pixels. That's probably slightly less than the camera in your mobile phone, for example. It can also take low resolution videos as well. But what makes it interesting is the fact that because you can upload custom code onto that ESP-32 chip, you can totally change its behavior and the way it functions. So for example, let's say you've got a PIR sensor. This is something that detects heat movement, and you can have that connected to one of the GPIO pins. When movement is detected, it triggers the camera to take a photograph. And perhaps you want to set this up outside somewhere, so this whole module will run off a single 3.7 volt LiPo battery like this one. So with that combination there, for example, you could set that up outside a bird box in your garden, and every time movement was detected, you could take a photograph of whatever birds are visiting your garden. Or maybe instead you want to create some sort of security system. So I've got a pressure pad here. This is effectively a very big switch that gets activated when someone steps on it. Well, if you connected that to one of the inputs instead, you could cause the camera to start a video stream, and it could also email you to say that the pressure plate had been stepped on. Log on here to see a live video of what is being recorded at the time. Or you could set it to a time-lapse camera, for example. So set it to wake up every minute, every hour, every second, however often you want, and save a stream of images to the SD card on board there. And then you could create a video at the end of all of the shots that have been taken. So there's loads and loads you can do that. It's really, really powerful. It's not very expensive. This only costs about £5. The only difficulty with them is because there's a lot of functions packed into them, they are a little bit tricky in places to get to work. They're not quite as straightforward as working with a typical Arduino. I've been using them for a couple of months now, and I've used them in a couple of different projects. So in this video, I'd like to both explain the project I've created and also some of the pitfalls and the problems I encountered on the way, and explain how to overcome them so that you can use these in your own projects as well. So to give you an example of it in action, here's the bird table in my garden, and I've pointed the camera at it to be triggered by a little PIR sensor at the top there. It's about 50 centimetres away, and I'm actually really surprised at the quality of the photos it took. You can see this blue tip here and the depth of focus in the background as well. And then at the base of the bird table I noticed this little crop of dandelions growing. So I set the camera to a time-lapse mode to automatically take a photo every 30 seconds, and then as the sun came up in the morning you can see the sequence of images as the petals open. And if you've been following my channel for a while, you'll know that I'm building an escape room in a box, and one of the new features I've just tried adding to that is one of these cameras here in the top half of the board. So this is actually triggered by one of the Arduino controllers which is running the game, and that sends a high signal down this cable here to the GPIO pin on the ESP-32, and that can trigger a photograph to be taken of players when the game starts, or when a puzzle is solved, or for any game event. Okay, so let's talk about the hardware. And what you probably find when you buy one of these modules is that it comes supplied without the camera connected to it. This is normally just sort of floating around in the bag separately. So the first thing you're going to want to do is to actually connect them together. So to do that, there is this connector in the middle of the board here, and you pull down slightly on this lever on the top, and that exposes just a row of contacts on the bottom. And on the reverse of the camera ribbon, you'll see that there's a row of contacts there as well. So we're just going to gently push the ribbon cable of the connector into that slot. You see this is a bit fiddly to do, there we go. And you want it to be lined up nice and straight, it doesn't go in too far, and then you simply clamp that shut in position there. And what that should do is that should create a nice secure connection with the contacts to the camera. You'll notice that the actual lens itself though is still quite wobbly. So what I've normally done now is just to put a little blob of sticky fixer or blue tack or something like that, just to hold that camera back and keep it secure against the back of the board there. Now you might find that your module was also supplied with an external aerial like this one, but it might not have been. I found about half of the units I bought came with an external aerial, half of them didn't. Now it doesn't matter too much because the board itself does have an internal Wi-Fi aerial that's built into it, like this one here. But it also has a little IPEX connector here, that's this round socket, and that is for connecting this external aerial if one was supplied, which in theory will give you a better Wi-Fi strength. Now the thing is though, it's not quite as simple as simply plugging the external aerial in if you want to use it and pulling it off if you want to use the internal one instead. There's actually a tiny little selector at the bottom here, and what it is, there's 3 contact points and there's a 0 ohm resistor that needs to bridge between 2 of them, and that selects whether you want to use the internal aerial or the external aerial if you've got one. Now one of the things you might have noticed from looking at this chip is that it doesn't actually have any USB connector on it anywhere. So in order to be able to upload code onto it, we're going to need another piece of external hardware. And one popular option is an FTDI programmer like this one. So this has a USB mini connector at one end. It then has a chip here which is a USB to serial converter, and it has a row of output pins that we can plug into the GPIO pins on the ESP-32 CAM board. And what this will do is this will effectively take USB data input, convert it into serial data output, and it will use that to program the board here. Now these are actually very handy little boards, and you can use them to program lots of chips, not just ESP32s like this one. And they can program both 5 volt and 3.3 volt devices. So before using one, the first thing you need to do is to make sure that it's set to the correct operating voltage. So you can see there's 3 pins here and there's a little jumper. So this one at the top is 5 volts, the one at the bottom is 3.3. So I'm just going to put the jumper across those 2 pins there to make sure it's set into 3.3 volt mode, because ESP32s run at 3.3 volts. And then you'll see that I've got the wires already plugged in here via a cable, and what I'm going to do is I'm going to plug the VCC output into the 3.3 volt pin here. I'm going to have ground, going to ground, and then I've got a receive and a transmit data line, and those are going to go into the transmit and receive pins on the ESP32 like this. So the way this is going to work is we are now going to plug the programmer through this USB connector here into the PC. We can go into our Arduino IDE or whatever other development environment you're using, select the target board and upload data through the programmer here onto the ESP chip. It's kind of like a pass-through that will convert incoming USB data into a serial connection. We'll connect to the serial pins here, and then back again we'll take serial data back into USB. Obviously with the serial connection you need to make sure that you connect the transmit pins from here to the receive pins on the ESP32, and the transmit from the ESP go to the receive on the converter and then back to USB. And once you've uploaded code onto the board, you can then pull this off again, and the code will be saved on the chip, and you can now power this however you want, through the 5-volt pin here or through the 3.3 volt pin at the top. Now, this is an alternative which I've only discovered more recently, and this is essentially exactly the same thing as the FTDI programmer, just in a slightly different form factor. And the point about this board is that it'll actually slot directly underneath the ESP-32 CAM module, like that. It, like the FTDI, now acts as a programmer, so we can connect to the USB micro socket here, connect that to our laptop and upload code. But also it's a really handy way to actually supply power to the device as well. So while we're talking about power, you'll see I demonstrated in the videos earlier one of these LiPo battery packs. So this takes a single 3.7 volt LiPo battery, but there's some circuitry on the back that will step that supply up to 5 volts with a 4 amp output, and also outputs 3.3 volt outputs at 1 amp. And it has a charger circuit as well, so you can actually recharge the LiPo battery while it is still in place through this connector here. And then it has an output at the top, which is for the 5 volt output. So one of the really handy things about this particular board is not only can you use it to program the ESP, but if I now just plug into the connector at the bottom here, that's actually a really convenient way of powering it as well from the 5 volt output of the device here. Now, just to clarify, I said that the ESP chip runs at 3.3 volts, which it does. However, I'm supplying 5 volts and letting the onboard regulator drop that down. And the reason is because the lower voltage output from here only supplies 1 amp. And I found that that's not enough current to actually drive the Wi-Fi and the camera and the SD card. All of these devices at once use quite a lot of current. So I found it's better to actually supply a 5 volt supply, even though that's kind of more than it really wants, but then let the voltage regulator here drop that down to 3.3 volts. That's the way I've found to get more reliable performance without risk of brownout errors and things like that. Now obviously the wiring is going to depend exactly on how you want to use this module. So rather than show you a complete wiring diagram, what I'll show you is some snippets of how to wire individual components together that I used in those projects there. So firstly is how to wire the FTDI controller to the CAM board in order to be able to upload code onto it. And I kind of demonstrated this in the video earlier, but I just wanted to reiterate it. So you have a selector switch normally on these boards, which you set to either 5 volt or 3.3 volt, and you want that to be set to 3.3 volts. And then you connect the receive line on the programmer to the transmit pin on the ESP-32, which is this one here. Then you plug transmit into receive, connect the grounds together, and VCC goes to the 3.3 input here. Now one thing to note, however, is that different programmer boards from different manufacturers come with different pinouts. So these two images I've got here, these are actually photographs of two boards with exactly the same functionality. They've actually got the same chip on them basically, except notice that in this one we have, starting from the top, ground, CTS, VCC, TX0, RX, and on this one we've got exactly the same pins but literally listed from bottom to top. So we've got ground, CTS, VCC, transmit and receive. So do be very careful when you follow the wiring that your pins may be in a different ordering. The only other thing to notice here as well is that when you want to upload code, you need to put the ESP-32 into a kind of programmer state, and to do that you connect GPIO pin 0, which is here, to ground. So I've just plugged the little cable in there, and having done that you hit the reset button on the board once. That will put it into programming mode where you can upload code to it. Once you've uploaded the code through the programmer, you can then take this off again, reset once more, and it will start running the code that you just uploaded. If you're using one of those modules which I showed, the programmer modules, that kind of happens automatically, or at least it should happen automatically anyway, so you won't need to manually do that, but you'll need to insert that cable there if you're using a programmer of this style. Now, in terms of using sensors or other inputs to trigger the camera, that's not quite as straightforward as you might think either. You can see that there's a number of GPIO pins on the ESP-32 board, but actually, as it turns out, a lot of them aren't available for use because they are shared functionality with either the camera sensor or the SD card. But using the code which I'll show you later on, it is possible to use pins 12 and 13 on the board here as either inputs or outputs. So with the example of the camera that was triggered by a PIR sensor, what I've got here is a PIR sensor which has got a 5 volt supply which is wired to the 5 volt pin here. It's also got ground and it's got an output in the middle, and that output line goes high when movement is detected by the sensor. Now you'd think that you would be able to plug the output of that directly into one of these two pins here like that then, but when I tried to do that I found actually that whatever reason the output signal from this was not enough to reliably be detected as a high input on the pin here. So what I've done instead is I've used an NPN transistor. So this is a BC547 transistor, which is a very cheap common component. It literally costs a penny. You can buy them in bags of thousands. And what that does is it means that when a very small current is applied at the base leg of the transistor, it allows a potentially larger current to flow from the emitter, which is a pin here, to the collector. So what I've done here is it's a little bit, you can think of it a little bit like a relay where you use a small load on one side of a relay to trigger a bigger load on the other, but rather than being electromechanical, it's purely an electronic component. So what we're going to do here is we've got our PIR sensor which is powered by 5 volts. That's going to give an output through this 2 kilo ohm resistor here into the base of the transistor, and so when this weak signal here, which I found that wasn't strong enough to be detected directly on a GPIO pin, but it is strong enough to turn the transistor on, and that's going to allow the 3.3 volt pin here, which is connected to the emitter, that's going to allow current from there to flow into the collector here and into the pin. So I found that was just a way to get the detection of these PIR sensors much more reliable than just plugging them in directly, which I'd seen used in some other circuit diagrams but just didn't work for me at all. Okay, so here's the code. Now, even though this is written for an ESP-32, you'll notice I'm using the Arduino IDE still, because that's an environment that I know a lot of people are familiar with, and if you've come from an Arduino background you can carry on using it to program ESP chips as well. The only thing you need to do is go into File Preferences, and where you see this line here that says Additional Board Manager URLs, you need to include the package that defines the ESP boards, which is this one here. Once you've done that, you can then come into your boards here, and you'll see that you have, in addition to the Arduino boards listed at the top of the screen here, I've got a ton of other boards as well. I've got some ESP-8266 boards, and I've also got some ESP-32 boards here. And assuming you're using exactly the same hardware as me, the one I am using is called the AI Thinker ESP32 CAM. So you select that as your target board, and from then on you can carry on using the IDE just as normal as if you were using an Arduino. So all my code listings, I start at the top with some includes. So these are external libraries that we're going to make use of. Now all these ones at the top are actually defined as part of the ESP development kit, so you don't need to download any of these extras, but they do define kind of additional features on top of the core functionality of the chip. So just to talk through what they are, obviously this is the core functionality. We then load a library that lets us access the camera, we're going to save photos onto the built-in SD card, so we both have the SD library itself and also a library to access a file system on the SD card. We're going to make a couple of changes to the way the system behaves in regards to its power functions, so that's what these three libraries are for. We're going to save some data onto the EEPROM as well. So the SD card, that's kind of like a storage for data, which is where we're going to save our images. EEPROM is like a very small amount of erasable flash memory, and we're going to use that to keep track of the number of photos we've taken so that we can increment a file counter each time. We are also optionally going to use a Wi-Fi network if it's in range. We're going to use that to download the current time and also to send an email with an attachment to the photograph on it. And the time function here will let us actually work out the timestamp at which each photograph was taken. Now this one here, this is the only third-party library we were going to use. So this is the one that lets us send emails. And there are several similar sounding libraries, so I will show you the one it is. If you go to Manage Libraries here, and it is the one that is called ESP Mail Client. So if I simply search for that, you'll see it is this one here. Confusingly, it is not the ESP-32 mail client. That's actually an older version of the same library. You just want the one that's called ESP Mail Client, and that works for ESP-32 and ESP-8266. So we're going to install that as well. You only need that if you want to use the email functionality, but I've included it at the top here. Okay, and then we get some defines. So these are kind of constant values that we're going to replace in our code that's going to alter the behavior slightly. So with each of the lines here, you'll see I've commented some of them and I've left some of them uncommented. So this is up to you to change, to alter the behavior that you want the code to have and what features you want to include. So the first one, this is what I mentioned about the EEPROM saving the number of pictures that we've taken. So you'll have like pick 1, pick 2, pick 3. And if you want to do that, then you keep this line here uncommented. We've got option to use the timestamp as well. Now, the ESP-32, although it's got a lot of onboard functions, doesn't have any ability to actually keep track of the current time. It doesn't have a battery-backed real-time clock on it anywhere. So if you want to record the timestamp at which a photograph was taken, which is a pretty useful thing to want to know, we're going to connect to an internet time server to get the current time. That obviously requires a Wi-Fi connection, however. So if you're talking about setting this camera up somewhere, you know, in the middle of a woods or at the bottom of the garden where you don't have Wi-Fi, that's not going to be an option. So I've left this as an optional inclusion if you want to use a timestamp, which is retrieved from an internet time server, but that does require a Wi-Fi connection to work. Likewise, clearly sending an email of the photograph is going to require a Wi-Fi connection as well. And then we've got two different modes that will actually activate the camera to take a picture. So you only want one of these uncommented. If you use this one, for example, you want to comment the other one out. So in trigger mode, this is where one of the GPIO pins, so I'm using GPIO pin 13, when that is set to a high signal, so that could be as a result of a button being pressed or a sensor which is reading a high value, or that could be another Arduino, for example, which is sending a high signal. When that happens on that pin 13, the camera wakes up and takes a photograph, and it does that every time that rises from low to high. Or alternatively, timed mode, this is where the camera wakes up automatically on a given schedule. So every 50 seconds, 100 seconds, 1,000 seconds, however long you want, it will wake up. And so this is for sort of time-lapse photography, basically. And then we've got some more defines here. So this is only relevant if you want to send an email, and these are the credentials that you're going to use to log on to your email account and to send that email. So we've got, first of all, the network that you're going to connect to and the SSID and password, and then you want to define the mail host. Now, I'm using a free Outlook address here. I would recommend that you don't use your primary email account, because if something goes wrong in your code, let's say that you set timed mode activated and you send you set a photograph every 2 seconds, let's say, and you email every 2 seconds a new photograph to your account, you'll probably find your email is going to get blacklisted quite quickly as being a spammer. So what I did was I signed up for a free email account, a Hotmail account basically at outlook.com, and I'm using that to send my photographs from. So that literally only takes 30 seconds to sign up for a new outlook.com email address. And if you do that, this will be the address of the mail server that you need to log on to. You can have a Gmail account instead, or any other email account. You'll just need to change the address here to whatever the SMTP server is for your email. Okay, then we get on some constants. So the constants are variables which are going to stay the same throughout the duration of the code. And the first section here, this is where I actually define some of the GPIO pins that are going to be used in the code. So, although it looks like the ESP-32 cam has quite a lot of pins, in practice not that many of them are actually usable, because quite a lot of them already have functions attached to them. So the camera itself and the SD card, and then there's various LEDs attached to them. So first of all here I've got an LED pin. And this is a red LED pan that's on the back of the board near the reset button. And we're going to use that just to show when the board is actually activated and doing something. So that's attached to GPIO pin 33, but we'll refer to it in the code as LED pin. On the front there's another LED, but this is a much brighter white LED. And this is the one that we're actually going to use to create a flash if we want to take photographs in low light, and that's attached to GPIO pin 4. And then, so these are both output pins. Then the trigger pin, this is going to be an input pin, because this is the pin which we're going to use to take a photograph if we're in trigger mode up here. It's when this pin gets sent a high signal, and it's pin 13. That's where we're going to take a photograph with the camera. That'll be our trigger. We also define a flash power. So if you want to use the flash that's at the front here, it's actually surprisingly bright for quite a small LED. So you can set it to any brightness you want between 0 and 255. But even if you don't want the flash on, you might find it quite helpful to set it to a very, very low value. And that's what I've done here. I just set it to 1 out of 255, because then it will kind of act as an indicator to show that the photograph is being taken. It won't really illuminate the scene at all, but it will just show that the camera is on and doing something. So that's quite a useful way of doing that, I found. Then if you are not in trigger mode, but if you're on timed mode, so this is where we're taking a photograph every regular number of seconds, this is how many seconds to wait in between taking a photograph each time. So I've put 30 seconds here, but you can put 1 second, you can put like 10,000 seconds, depending what it is you're trying to take a photograph of, basically. Now here I've put a delay time in milliseconds, so this is something you might need to tweak yourself later. I'll explain exactly how that's used later, but essentially when the camera first wakes up, it does some kind of automatic initialization and calibration routines. So there's an auto exposure mode, for example, but that exposure only works if it's had a bit of time to actually measure the light in the scene and things like that. So normally when the camera's triggered, you obviously want to take a photograph as soon as possible after the trigger to capture whatever it is. But at the same time, if you take the picture too quickly, you'll find that the camera hasn't had enough time to properly configure itself. So I set this to 3000 milliseconds, so 3 seconds after the trigger first gets detected before it takes a photograph. And I found that worked pretty well, but you might want to adjust that up and down to get a quicker response. But if you take it too small, you might find that the auto exposure doesn't work. But I'll talk about that in a bit more detail when we get to the exposure and the sensor settings later. Now we have a couple of globals. So this is the picture number that we take. Like I say, this is going to get incremented every time we take a picture. And if you choose to number the files according to the latest picture, then it will get saved as part of the file name on the SD card. And then this is a path object which we will use to save the latest photograph taken to the file system. That will be the path it gets sent as. If we are sending an email, if that's one of the functions that we've chosen to do, we'll also create a global variable for the session that we connect to the SMTP server, and we define a callback function. So a callback function is a function that gets called, unsurprisingly, when a certain event happens, and in this case that event is sending the email. So this callback at the top here, what we do basically is it's like a status report after we've attempted to send an email. So this will be called automatically by the email sending function. It will print the status of the SMTP request, basically, whether it was a success or a failure, and some details about, if it was successful, who the email was sent to, the subject and the date, time it was sent, and things like that. Now that is the only callback. Now we have one other interesting function here, and this is a sleep function. Now to kind of explain why this is here, I'm just going to jump ahead a little bit first. So normally in most ESP or Arduino code, you're probably familiar with having a setup function, which is run once when the code first starts up, and also a loop function, which is something that loops round and round while the code is running. Well, one thing you might have noticed as I scrolled very quickly down here is that in this particular program, almost all of the code is contained in the setup function, and there's actually nothing at all in the loop function. We still do have to have it there because otherwise the code won't compile, but actually nothing happens. And you kind of think, well, hang on a minute, if there's nothing in the loop function, what is it that makes the camera do these functions? What is it that triggers a photograph to be taken, or to send the email, or to wake up when this high signal is received, or the sensor goes? And the answer is we're going to use an ESP feature called deep sleep. Now this is really, really useful for when you're creating battery-powered projects particularly. It's less important if you're running on mains power, but if you're creating any kind of portable kind of project and you want to reduce the current consumption as much as possible when it's not doing anything, and the way to do this is to sort of create this low power, nearly hibernating state of the chip, and it shuts down all of the non-essential functions. So you know, the Bluetooth, the Wi-Fi, all of this gets shut down. And the only thing that will wake it up again is a very specific sort of signal that you define before you send it to sleep. So to talk that through, when it wakes up again, by the way, what it does is calls the setup function again, just as if it had been turned on for the very first time. So the way that our code here is going to work, we're going to have the device wake up when it first gets turned on, perform all the setup actions, then it's going to go to sleep, and it's only going to wake up again when a trigger occurs and call setup again. So we never really get into the loop function. That never happens. So the sleep function, this is what happens when we go to sleep. So we'll have a look what we do. The first thing we do is we define the trigger pin, and I'm defining that as an input pull down. Now this is another feature which if you're used to Arduino coding you may be less familiar with. On an Arduino you can define any of the GPIO pins as either an input or an input pull up. So an input means it is just floating signal, it has no particular state. An input pull up, well, that means it uses one of the onboard resistors to pull that signal up to a high value. And what you then normally do is you have something like a button which connects it to ground instead, that pulls it down low. Well, if you're on an ESP, you do have pull-up resistors, but you also have pull-down resistors on certain pins at least. And in this case, we're going to use the pull-down on the trigger pin. What that's going to do is it's going to keep the when we do a digital read on this pin, if there is no input to be detected there, it's going to make sure it reads a low signal. It's not just going to be an arbitrary floating signal, it's actually going to pull it down to ground, to low. And only when that gets pulled up to 3.3 volts, that's when we'll record a high signal on that input instead. So that's the first thing we do before we go to sleep. We'll make sure that the trigger is set as a pull down. The next thing, this is a bit complicated as well. So this holds the setting, holds the pin mode of a GPIO pin while it's asleep. Remember I said that when it goes into sleep mode, the ESP kind of enters this very low power state and it turns off all its non-core functionality, and that can actually cause it to kind of forget the settings that you'd assigned to certain pins. They restore back to their defaults. If you don't want that to happen, if you want it to remember the state that you set a certain pin to while it's asleep, you can call this hold function here. So what we're going to do is we're going to hold GPIO number 4, which is our flash on the front. We're going to hold that in the state it was in so that we don't accidentally get the flash turning on when we go to sleep or something like that. We'll also turn off the LED on the back of the board as well. Now confusingly, this is an active low LED, so to turn it off we actually write a high signal to it. So this is all kind of getting ready for bed. We'll put the trigger in the right state, we'll make sure it remembers the flash on the front, we'll turn the LED on the back off, and then what we need to do is we need to basically set our alarm clock. What are we going to do to wake up again? Well, we've got two choices here. If we want to use the trigger mode to wake up, that's where we are listening to our GPIO number 13 pin, and we've got two options here. We might want to wake up when that goes high, and this is the line of code which I'm using in all of the projects that I've actually built. This is the way I'm using it. So if you're using a PIR sensor, for example, that typically goes high when it detects movement. So if you're using a PIR, that signal line is connected to GPIO number 13, you want to wake up when that signal goes high. Similarly, if you are going to write a high signal from another Arduino or from a button or something like that, you want that. Alternatively, you could comment that one out and have this one instead. So this would be exactly the same, but this is where it goes low. Now the only thing to note here is if we're waiting for the pin to go low, then we want to have this as a pull up instead. So this normally keeps the state of the pin high, but then we wait for it to go low. Or alternatively, you want it the other way around. We normally keep it low, and instead we'll wake up when it goes high. So they're just two different ways of setting the same logic basically, but you probably want it to be this way round. Certainly if you're using a PIR sensor, that's how you want it. Alternatively, maybe we want to set our alarm clock to wake up after a certain amount of time. So in that case we call this function instead, so we call the sleep enabled with a timer wake up rather than with an external wake up. And when do we set our time for? Well, it's the time-lapse interval which we defined in our constants at the top of the code here. Now we gave that value in seconds because I just found it more convenient to type in seconds. But the timer wake up function expects that to be in microseconds, so we have to multiply by 1,000,000 to get that in the right interval there. So we specify our alarm clock, and the final thing we do is we actually tell the device to go to sleep. So having chosen our way of waking up, making sure that if we are using a trigger pin that we have set that to the right mode as well, we've turned the lights off, now we actually go to sleep. And what will happen then is that when either of these two events that we chose here wakes the ESP up, it will go into the setup function. So that's where we now look. Okay, so we have looked at the constants, the mail callback, the sleep function, all the things. Literally all of the rest of the functionality of this device, absolutely everything else it does, is in this setup function here. Now, some coders will say that that's not a particularly elegant way of doing it. If you've looked at some of the examples that come with the ESP-32 camera, you'll see that they actually come with lots and lots of different files that, subroutines and modules that divide all the functionality into different files. And arguably that is a better way to arrange complex code, but I think in terms of explaining what's happening, it's actually easier to see just this, it's slightly monolithic, but it literally follows it in order, the steps that happen in chronological order, all in one place. So I'm going to keep it like this because I think this is actually easier to explain all the different steps involved. None of them individually are that complicated, so it's just a matter of stepping through them and explaining what they do. So here goes. Once again, we start up with very simple visual indication that the device is doing something. So we'll turn on the LED that's on the back. So this is the little red LED on the back. And remember I said it's an active low LED, so we actually write a low value to it to turn it on. Now, this one here is slightly complicated. Remember I said at the top we were including some system settings libraries, these ones here. So this particular project, the camera, uses an awful lot of power. So anything up to about 2 amps, I think, peak power. And the ESP is only a tiny little chip. It's very powerful, but it only so much it can really provide. And if it senses that too much or not enough current is available rather for the ESP, and that can happen when the camera is drawing too much power from the power supply, it kind of shuts the ESP down. It's a safety feature, and it's a very good safety feature. I'm going to be a little bit naughty though and disable it because I found it's a little bit too eager to shut itself down. So as soon as you try to actually activate the camera, the first thing that happens is the ESP shuts itself off because the camera's drawing all the power. So I've written a caution here just to be aware of what this line of code is doing, because effectively I'm overriding a safety feature that comes in the ESP that is designed to stop it from experiencing a brownout if there isn't enough power to supply it. But I found that was necessary, and it hasn't caused any damage whatsoever to any of my ESP chips. When I'm running on battery power otherwise, it was just always shutting off all the time. I think it's just a little bit too eager, effectively, the safety protection, so I'm going to turn it off. I've created a serial connection just as completely standard there so that we can get some debugging information. And now we're going to configure the camera hardware. Now, if you're using the AI Thinker ESP-32 cam like I am, you don't need to change this at all. I've just included it here because there are a couple of slightly different boards available, and if yours is wired differently, then you'll have to change. So this is the pin on the ESP-32 chip and the corresponding pin on the camera. And I mentioned earlier that although the ESP's got a lot of GPIO pins, lots and lots of them are being used by the camera already, as you can see here. So pins 5, 18, 19, 21, 36, 22, 0. All of these pins here are being assigned to some function on the camera, and that generally means we can't use them for any other function in our code. So there's actually not that many pins available. But yeah, if you're using the same camera as me, you don't need to change those at all, but I've left them there so you can configure them if necessary. Now these things you might want to change, however. So this is the configuration really of the quality of the photograph we're taking. So I'm specifying that we should take a UXGA, which is the highest resolution photograph that the camera is capable of. That's 1600 by 1200 pixels. Now that's only possible though if your board supports something called pseudo RAM, which is like an extra chip of RAM that's on the board that enables it to work with these higher resolution images. If your board doesn't have that, what we'll do is we'll default down to a lower quality and a lower resolution picture instead. And here's some of the alternatives you can specify, so QVGA, VGA, SVGA. But if you're capable of doing it, I suggest this is the largest resolution, and you can also select the quality settings as well. Okay, so that's the camera configuration. Now what we do is we configure the flash on the front, and because we want to be able to vary the power of that flash, we need to attach it to the LED driver, the PWM driver for LEDs on the ESP. So what we do here is we specify PWM channel 7 with a refresh hertz of 5000 and 8-bit resolution. So this is setting up the PWM controller. Again, this is a little bit different than if you're used to using an Arduino. On an Arduino, you simply call analog write. On an ESP, it's slightly different. You've actually got different PWM channels, which are going to assign to different pins. And what we're going to do here is we're going to assign this sort of PWM driver that we just hit to GPIO pin 4. It's all a bit complicated if you haven't seen that before, and it's not very well explained. Apologies for that. But what it then means is that we can then finally call LEDC write, and instead of writing the pin directly that we want to do a PWM signal to, what we do is we write the channel of the LED controller, and that channel has previously been attached to the pin here. So it's kind of one more step removed from the pin than you might be used to. But what we'll do is we'll specify the flash power, so that might be anywhere between 0 to have the flash off and 255 for maximum brightness. Like I said, I quite like using a very low power of just 1 or 2 just to light the LED up and show that a picture is being taken. Then we will have a little pause here. Now this is the first of a couple of little pauses that we're going to introduce into the code. Remember, the one I said at the top was about the auto exposure settings of the camera. Well, this one is to make sure that the I2C interface has initialized before we try to turn the camera on. If in your code you get some error about something like camera model not supported or camera not found or something like that, what it probably means is that you're trying to initialize the camera too soon after the code has started running. So this delay here, this is just a 1/4 of a second delay, just to make sure that the interface is up and running before we try to turn the camera on. Assuming that's successful though, we will then have access to the camera here. If it's not successful, what you notice here is we just go back to sleep again. So this was the sleep function that we defined up here, and this will go back to sleep and then try to wake up again whenever the trigger is next detected. So every time we fail in the code, instead of just crashing out or giving up or something like that, what we say is, okay, we'll go to sleep and try again next time, essentially. But assuming that it was successful, so we've waited a bit for the I2C interface, then we've turned the camera on, then what we can do is we configure some settings about the image itself. Now, I've included all of the different settings you can configure here, but I've put these as their default values for now. So in practice, you could actually comment out this entire section. It would have absolutely no effect because all I'm doing is overwriting all these different settings with what they were default set as anyway, but I've included them because I wanted to demonstrate the different things you can set, and actually there's a surprising amount that you can configure. So we start at the top with things like the gain, the exposure correction, and the white balance. Now by default these are all set to automatic mode. So this is automatic gain, this is automatic exposure, automatic white balance. If you want to specify a manual gain, the first thing you'll need to do is to disable the automatic gain like that, and instead, let's say you could now put a manual gain value here, so somewhere between 0 and 30. But you do need to disable the automatic gain first. You can't just set a manual value here, otherwise what you'll do is you'll find it will be overridden again by the automatic the value here. So we've got gain, exposure, we've got some white balance, and then we've got brightness, contrast, saturation. There's even a handful of built-in special effects. So if you want a sepia effect or grayscale or negative, things like that, you can put them here. You can flip the image over vertically or horizontally. That's quite useful if the way that you actually mount the camera is not the way up you want the photograph to be taken, for example. There's two at the bottom. If I'm totally honest, I don't even know what those do. I just found them in the ESP camera library. So if you happen to know what those do let me know. That would be great. But these are all the values you can set if you want to correct the image. And yeah, again, I said here that what we do now is we actually wait a little bit of time before grabbing an image from the camera. And the reason for that is because by default we are using the automatic settings. If you were to set these to manual instead and to explicitly set a gain and an exposure and a white balance level you want, then you can delay your startup time here, because that's the thing that takes the time to happen, is configuring the values of the automatic settings. Anyway, so either way you've done that, what we do is we initialize some memory for the frame buffer, so the in-memory picture that we're going to take, that's in the frame buffer. Then we wait this bit of time just to make sure that the sensor has grabbed the automatic exposure settings, and then we actually try to take the picture. So, oops, I just commented that out. This very innocuous line here amongst this entire sea of code, this is the one that actually takes the picture. Doesn't it look very plain and not really like it does very much at all? But that's the important one. And then what we can do is we can check the result of that to make sure that we actually got some data from the camera. If we didn't, once again, we'll say, okay, go back to sleep, try again next time. But assuming we did get some data from it, we can carry on. We go on to the next step. So whether we had the flash on as bright as possible, or whether we only had it on a tiny bit, before carrying on, we can definitely turn it off now. So we will write a 0 value to our 7th PWM channel, and that's the one that's controlling the flash. And then what we're going to do next is we're going to start building up the file name that we're going to use to actually save our brand new photograph to. So at the moment it's still only being held in memory. We've got this frame buffer which is just a series of bytes in memory, and we're going to save it out to the SD card. But before we do that, we need to decide what we're going to call it. So if we are using incremental file numbering, this is where we just have a value that increases every time we take a new photograph, and we use that to name the file. So to do that, we are going to use 4 bytes of EEPROM memory. That should be plenty to store a big number in to save our photos, unless you're going to take a huge amount of photos. That should be plenty. If there's already a value there, then we'll grab it and we'll increment it by 1. And then what we'll do is we will build up our path. So we've already got a / pic, and then we will put the new picture number after it's been added by 1 onto the end of it, and then we'll save the new value back to EEPROM. So we grab whatever was there, increase it by 1, use that to name our file, and then we save it back again. I have used EEPROM a few times before in my different projects, probably not as much as I could actually. It's very, very useful if you want to persist small pieces of data on an ESP or on an Arduino as well. Just very, very small values. It can't be used to store sensor readings and lots of data, but things like configuration values, it's actually really useful. And the way you do it is you kind of create this copy in memory of what the EEPROM value is, and then you write it back once you've finished using it. So you do have to remember to commit back to EEPROM, because this put command here doesn't actually save it back, it just alters the kind of in memory value, and then this actually saves it back. So important to remember to commit once you're using any EEPROM data. Okay, so that has modified our file path, or it might have modified our file path. The next thing we need to do is we need to turn on the Wi-Fi if we need it. So if we want to grab the timestamp now at which the photograph was taken, or if later on we're going to send an email, in either of those cases, we're going to need the Wi-Fi activated. So here we've got some fairly standard code on an ESP to connect to a Wi-Fi. We'll define that we are acting as a Wi-Fi station, so we're not a hotspot, we're going to be a client connecting to an existing Wi-Fi network. We'll give ourselves a name. In this case, this is the camera I set up on my bird table outside, so I've called it bird feeder cam. And we have a counter of the number of attempts we've made to connect to the network. And then we actually try to connect. So Wi-Fi.begin with the specified SSID and password. And then what we do is we wait basically to connect. Now, if you've got a good Wi-Fi signal, this sometimes gets through on the first count, sometimes it takes a little bit longer, but this will basically loop round and round until either it gets connected or it exceeds 10 iterations through this loop. And like I say, if your Wi-Fi network is a bit slower to respond, you might want to increase that number there so it gives it a longer timeout basically. But in between each time it waits half a second and then tries again. If in that time it did get connected successfully, then we'll just dump some information out to the serial monitor to say the IP address that we got assigned and also the strength of the Wi-Fi signal. If we didn't get to connect to the Wi-Fi network but we wanted to because we were using one of these features, then again we say, okay, go back to sleep, try again next time. Okay, so we've reached this stage. Now at this stage here, what we know so far is that we have successfully taken a photograph, we have successfully accessed the picture number on the EEPROM if we wanted to, we've successfully turned on the Wi-Fi if we wanted to. So now if we want to grab the current time to append that onto the end of the file name, that's what we do in this section here. So I am in the UK, so my offset from GMT time is 0, and also we're not currently got any offset from, if you have daylight saving time or something like that as well, you can define an offset here. So this will be you will need to customize this wherever in the world you are, and whether you are currently observing daylight savings times or not, you can enter values here which are in seconds different from GMT, so they might be quite big values depending on where you are. Because the time server that we now specify, so we're going to call this config time function, will pass in our two offsets and we will grab a time from, I'm using pool.ntp.org. You could also use one of these alternative servers instead, so time.windows.com or time.nst.gov. There are other ones as well. So these are servers which exist on the internet and their only purpose is to tell you what the time is. Very useful little things as it happens. So we'll try to configure the time, and then what we'll do is we will create a structure to hold that time in, and that will make it easier to kind of grab the different components of it. So rather than it just being a total number of seconds since the epoch in 1970 or whatever, we can grab bits of it. So we'll try to grab the time and put it in this time info structure. If we fail, guess what? We go back to sleep. If we succeed though, what we'll do is we'll output to the serial monitor what the current time is, and these little kind of placeholder values here, these specify the elements of the time that you want to show. So here I'm showing the day name, the month and the day of the year, and the hours, minutes and seconds. That's what I'm writing to the serial monitor. But for the purposes of naming the file, what I'm going to do is I'm going to write the year, then the month, then the day, then the hours, minutes and seconds. And I'm going to append that onto the path that we've got already. So we may already have appended to our path. If we're choosing the incremental file numbering, we might already have a picture number on, but we might not. We might just be looking at pick at the moment. Either way, what we'll do is onto the end of that we will add on a timestamp that is the year, month, day. And you can format this differently if you want. So I've given an example that shows some of these other formatters here that you can use to retrieve elements of a timestamp and put them on the file name there. Now that we've finished adding elements to our path, we'll add the file extension on the end as well. So we'll just slap a JPEG extension on the end of it. That is the file format that our frame buffer is in. So when we come to save this file, it is actually going to be a JPEG file, and we'll give it the right extension to make that clear. Okay, so we've finished setting our file name. Now we need to save it to the SD card. So to do that, we're going to call the SD begin method. Now this is a bit confusing because I'm calling it on the mail client object. You remember that mail client was something that we imported up here, which allows us to send emails. But those emails allow you to include attachments that were saved on the SD card, rather. Sorry. So in order to let the mail client access the SD card, I'm calling the SD begin method from the mail client object itself rather than from the SD card library. So that might seem a little bit confusing, but it just makes sure that it sets up that kind of link from the mail client to the SD interface, basically. The SD library itself also defines a begin method, but we're not going to call that one. We're going to call the mail client one. And these are the pins which the SD card uses. So as if we hadn't already assigned enough pins when we were talking about the camera set up here, so all these pins are defined by the camera, we're now also going to define a load of other pins which have to be used to access the SD cards. We're using 14, 2, 15 and 13. But hopefully that's alright. Again, these are the correct values for the board I'm using, which I'll include a link to. Your board, if you're using a different model or manufacturer, might be slightly different, but hopefully they're the same. If we can't access the SD card with those settings, then we print an error message and we go back to sleep. But assuming we can, we carry on. So now we try to access the file system on the SD card. So we create a new file system object and we tell it that we're going to be using the SD format to do it. We will try to open the file at the path that we have built. So this was the path, remember, was all that thing that we started with pick, and then we added an extension, or we added a timestamp, then we added the JPEG extension. What we're now going to try and do is save the file to that path. So to save a file, you actually call the open method, but pass in the file write sort of parameter at the end there. And assuming that was successful, what we will do is we will then write the contents of our frame buffer into that file that we opened for writing. I'm not even going to say this anymore, but if it was unsuccessful at writing, we go back to sleep. But yeah, so what we do here, we access the file system, tell it that we're using the SD card, we open the file that we have created, so the unique path for this version that increments every time, we open it with the write mode, and then we write the buffer values and the length of the buffer we write into that file, and then we just put a little message to say, hooray, we saved the file, and then we can close it. And now that we've finished working with the camera as well, we've saved the frame buffer we had, we can also release that from the ESP camera. So all this, up to now, we've just been holding in memory the whole time the bytes of our image data, but now that we've successfully written it to the SD card, we can release all that memory that we've been hanging on to, that's been holding on to that image, so we can release that. And we can take a little breath. Phew! That's just to let everything stabilize. That probably doesn't even need to be there, but I just like the idea of the ESP needing to breathe at that time. Okay, so we've written it to the SD card, and maybe that's all that needs to happen. But if you chose that you want to get the email sent to you now with that attachment as well, then we will need to step through this bit. And again, it's not too hard, it's just a bit verbose, there's lots of it. So SMTP, where you set debug mode on, you don't actually need to do that, but I find it's pretty helpful. It gives you a lot of output because there's sort of various steps involved here, and if any of them fail, it's useful to see what happened, particularly when you are sort of first trying to get this to work. So you first of all, we define a session. So there's kind of various nested objects within the email client functionality, and the largest one of these is the session, and the session relates to the host and the port and the author email. So this is our account from which we're going to send the email. So we define a session object and we configure those values, most of which were defined in the top of the code here as well, at the top of the code. Then what we do, now that we've got a session, well, now we need to create a message within that session. So we set the name of who this message comes from and also the email that it comes from. We set the message subject and we add recipients who are going to receive this message as well. And you can add multiple recipients. You can also add CCs or BCCs to your email as well. And we add whatever the text content we want to be to your message. So I've just got some plain text here, but you could make this more interesting if you want. And we specify the encoding format that the message comes in. So all this here, this is just like what you do when you open up Gmail or Hotmail or whatever and you type your new email to someone. These are basically the fields that you would enter when you're writing an email to someone. And then we define the attachment that we're going to add to the message, which is part of the session. So the attachment, well, this is going to be the file that we've just saved onto our SD card, isn't it? So we'll define an attachment, we'll call it ATT, we'll give it a file name and a MIME type, so it's going to be binary data, so octet stream. And then this is the important one because we need to tell the mail client where it's going to find the data to include as part of this file, and it's going to be the path again. So this path that we've been using all along, we built it up, we called it here when we saved the file to the SD card. So we're going to call exactly the same thing again to tell the mail client where to find it on the SD card. We'll just use exactly the same value. And then it's on the SD, it is encoded in base 64. And then this line here adds the attachment to the message above it. So we now have a message containing an attachment, and what we need to do is to send that to the session. So we've got two steps here. First of all, we try to connect to the SMTP session with the variables that we defined up here. And then if that is successful, what we then do is we then try to send the mail. So again, we pass in a reference to the SMTP server and a reference to the message that we've just created up here, which, remember, contains the attachment as part of it now. And hopefully that's successful, but if not, guess what? We go to sleep, we go to sleep. And then we finally get to the end of the code. So this is the last line that we need. This send mail sends the mail. So now we've finished all of our Wi-Fi functionalities. We can disconnect from Wi-Fi if we were using it. We can turn the Wi-Fi off. And for the final time, we can go to sleep. And so whatever actions were taken, depending on what features you chose, right at the top of the code here, remember half an hour ago, whenever it was I was talking about it, so you can define these different functions up here, and depending on which ones you have commented and uncommented out, different sections of this code will be executed from top to bottom. But essentially they literally just follow through the code in order. We configure the camera settings, we turn the camera on, we take the photo, and then we either get the new file number to assign to the photo, or alternatively we connect to a time server and get the time, and then we save the file to the SD card, and then we send the file from the SD card via email, and then we turn the Wi-Fi off, and then we go to sleep. And every time we go to sleep, again, remember we looked at this function before,
what we do is we just specify the conditions on which we want to wake up again. So we make sure we've got the pins in the right state, and then we either wake up when that pin goes high or when it goes low, or after a certain amount of time has elapsed, and then we go to sleep here. And this will now put the board into a very low power state. All of that functionality will be turned off, and it would only wake up when these events happen, at which point it will run through this whole setup code again and take another picture.
So hopefully this video has given you an insight and let me pass on some of the things I've learned from using these little ESP-32 cam boards. Like I say, they're not going to win any prizes for best photograph competition, but they're so small and they're so cheap. I mean, I literally bought a box of, I think, 5 of them for about £20, that you can just play around with them and try using them in different projects. So whether you want to create a wildlife camera in your garden, or maybe you want to create like a smart doorbell system that takes a video of anyone that comes to your door, or like me, whether you want to try to put them as part of an escape room prop or puzzle that takes a photograph of players when a certain game event happens. Hopefully I've been able to give you the idea and some of the knowledge that you'll need to be able to kind of run those kind of projects. I'll copy the code I've used and the wiring diagrams and things like that. I'll probably put them onto my GitHub account later so you can see them there. I'm only able to create these videos with the support of my Patreon donors, so I'd like to say all thank you very, very much for continuing to support me. I know normally the videos I make are slightly more escape room puzzle focused than this, but I hope you felt that this was similar enough that there is a kind of knowledge that you can use here and take it into an escape room context. In my next video, I will probably be going back and maybe even finishing off the escape room in a box I've been making, which has been going for a little while now. So if you're interested in finding out more about what's gone into that, please do follow along, and I will look forward to seeing you in that video next time. Okay, cheers, bye.